So this is Wednesday, October 28th. This is Discrete Math 3050, just a general discussion meeting. Now, before I start talking about stuff that I thought I might talk about, let me start by asking all of you if you have questions about stuff that you would like to have discussed. I'm rebelling today. Our son went back to in-person high school classes starting yesterday, and so it's now quiet upstairs, so I decided to not be in the basement. Well, so the material for this week is sections 9.1 and 9.2. 9.2, the video for that, I'm just starting to edit. It should be posted this afternoon. And you'll see that there's quite a bit more stuff in 9.2, not difficult stuff, but more stuff, more variety of examples. The underlying math is actually very simple. There are only a couple of math concepts, and that really goes for section 9.1 as well. There's not that much introduced in section 9.1. I think what I'm going to do, since I haven't put out that video for section 9.2 yet, it'll be out in the next couple of hours, next few hours. I think I won't discuss section 9.2 in this meeting. I'll just discuss 9.1 topics. Oops, that's my computer making all sorts of noises at me. So I'm going to switch to a blank document. I'm going to share. Let's see. Share. Oops. Oops, I screwed up here. Hang on. There. Can you all see this fine?
Yeah.
Okay.
Yep.
Now what I've got to do is I've got to flip my computer over. Let me see, so I can write on the, I have to flip my laptop on its back so that I can write the normal way. All right, so you're still all able to see that?
Yep.
Okie doke. Well, let me get my list of stuff that I wanted to discuss. Oops. Having trouble getting the right pen here. So section 9.2 is just the intro to counting and probability. So we have these main tools in this section. We have, first of all, the idea of sample space. So a random process is a process where there are a bunch of equally likely outcomes. And the sample space is the set of all possible outcomes. And then we have an event. which is just simply defined to be a subset of the sample space. Now, remember that the probability of an event is denoted that way, and it's computed by doing this. Now, I want to stop there and ask you all. There's something that I've neglected to say here that's actually very important. What qualifications do I need to add to this? Well, the trick here, what's subtle here, is this. This idea of probability uses these expressions that stand for the number of elements in the set. Well, that means that those sets have to be finite. Of course, if the sample space S is a finite set, then the event E that's a subset of that is also going to be a finite set. So in that case, you can talk about the probability in terms of the number of elements in the set. Now, if you don't have finite sets, then you can still talk about probability, but we don't do it in this section of the course. You know, for instance, if you ask this question, if you choose an integer at random, what's the probability that it's going to be an odd integer? Well, it's going to be a 50% probability, or the probability will be 0.5, but you can't talk about the number of integers and the number of odd integers because those are both infinite sets. So in the situations where you have infinite sets, there will still be an idea of probability of events, but it won't be achieved by counting the number of elements in a set. In those kinds of situations, different kinds of techniques would be involved. Now, let me see if I can. Oops. See if I can add some pages to this document. I left my keyboard at school, so I'm having trouble here getting stuff. All right. Now, I talked in the video for section 9.1 about the idea of illustrating sample spaces and events whenever possible. So the official description of sample space is that it's a set, and so the description of a set is in terms of a set bracket and listing all the elements in the set with commas in between them. An event is a subset of a sample space, so an event is also a set. So to describe an event officially, you would use set notation, but it's much more helpful to actually to have some kind of picture of the event. So even though and a picture of the sample space. So even though they might not be official set notation, it's still useful for solving problems. So let's do an example involving drawing colored balls from an urn. So the urn has, say, 2 red balls And green balls, let's say 3 of them. And suppose we're drawing 2 balls with replacement. So I discussed this in the video, the way of illustrating that the sample space could be this. The left, we could draw a table. Where the row heading indicates the first ball drawn. And the column heading indicates the second ball drawn. Now, who can tell me what would be the probability of getting exactly 1 green ball?
Well, 0.36. Hello.
So how did you get that?
The question is only get green, right?
Well, so you're choosing 2 balls without replacement. Oops, sorry. So the event E is that exactly 1 of the balls that you draw is green.
Is it 6/25?
Wouldn't it be 12/25?
Great. So which cells should I fill in to illustrate this event?
Both of the red cells on the left over with the green cells like in the column, and then also the green cells on the left with the red cells from the columns.
Exactly. So these cells in the table represent the event that exactly 1 of the balls chosen was green. And so so the probability would be 12/30. In other words, 2/5. Now, how does this change if we if we have no replacement?
I'm sorry, why is it 12 over 30 instead of 12 over 25?
Ah, because I'm having a brain fart. So in fact, it's just 12 over 25. Good. So now in another scenario, let's choose 2 balls without replacement. So how does that change all this?
You won't be able to have any of the boxes where you draw the same ball twice, so essentially you won't be able to have like the boxes in a diagonal from
Great.
the top left won't be able to be an option.
So let's bring this over here and let's shrink it a little bit. So in this second scenario, we have to gray out, oops, the diagonal. So in this second scenario, for the same event E, we still have the number of elements in the event being 12, because they are not affected by that diagonal being gray, but the sample space is smaller. It's only got 20 cells because we got rid of those, we grayed out 5 cells. So the probability of E is 12 over 20. So in other words, it's 3/5. So the probability actually goes up. Now, I want to talk about more stuff in 9.1, but actually this is a useful time to go on and talk about 9.3. So oops, 9.2. So in section 9.2, we deal with situations where a two-dimensional table is not a good way, is not sufficient for illustrating. So one of the topics in section 9.2 is situations where a table can't be used to illustrate the sample space. And so a good example of that would be, consider this same urn. As in the previous example. And so let's consider drawing 3 balls with replacement. So that means after I draw a ball and I record its color, then I put it back and I draw another ball. So how do we illustrate that? Well, we can't do what we did with these tables, where we have the first ball as the row heading and the second ball as the column heading. So one thing we can do is to use what's called a possibility tree. Now, in the video that's going to come out this afternoon, I'll discuss the way that I like to do possibility trees as opposed to the way the book does them. It's worth watching that video because in other books I've seen possibility trees done different ways, and when I do them myself, I have my own preference. But for the purposes of this course, I'm going to stick to what the book does. So what I'll do here is what they would do in the book. So what you do for a possibility tree is you have dots and line segments connected to illustrate sample spaces. So I'm going to start with a dot that's just the starting dot. And then I'm going to branch and have the result of choosing the first ball. So what are the results that we can have from that? We can have oops, that's going to get too crowded. Now, once we've chosen the first ball, that ball gets put back and we choose another ball. Well, that means for each of these, we're going to have 5 possible outcomes. Oops. So each of those represents one of those 5 balls. I'm not going to fill in all these. Oops. So there's the result of the second ball. And notice there are 25 dots there, so it's already getting kind of crowded. So this is maybe not the best example to illustrate a tree. But we could, if we had a bigger sheet of paper, we could show the third ball. And so for each of those 25 balls, there'd be 5 more balls. So I'm going to draw just one set of so you can see that there will be 25 dots arranged vertically. So so again, you can see that even though it gets crowded, it is possible to illustrate on a 2-dimensional drawing this sample space involving 3 balls. And so so a single outcome that is a choice of 3 balls would be something like this. That path would represent this choice of balls. So the red ball R2 was chosen first, and then the red ball R1 was chosen second, and the green ball G3 was chosen third. Maybe I'll color code those just because I like my colors. So the sample space can be illustrated with a drawing like this. Of course, it could also be illustrated by, could be listed explicitly by showing a set that shows all of these strings like that, strings of 3 of those characters chosen from this collection of 5 characters. So in section 9.2, for the homework that's due tomorrow, Thursday, you'll discuss possibility trees. Now, with possibility trees, you can also illustrate situations like the situation without replacement. Well, we could illustrate that by copying this whole diagram. Let me copy this and move it down. So to illustrate the situation, the sample space where you're drawing without replacement, you would have to take into account that you can't draw the same ball twice. So if R1 was chosen as the first ball, then R1 can't be chosen as the second ball. So this dot would not have a segment connected to it. If I had labeled these, in fact, I could label these more clearly. Maybe make this bigger. My possibility tree would have that first dot missing, and on this branch, that dot would be missing, and on this branch, that dot would be missing, and on this branch down here, the bottom dot would be missing, and then in this middle branch, well, let's see. The red ball R2 was chosen, and then the red ball R1 was chosen. So that means that for the third ball, neither one of those red balls would be available. So possibility trees are very helpful, are very good for illustrating sample spaces for random processes where the options for later sets are different depending on, the options for later steps are different depending on what results were chosen for the earlier steps. So again, keep your eye out for well, you'll have lots of examples involving possibility trees in the 9.3 stuff coming for tomorrow. What I want to talk about now is counting elements of lists. So let me just pose a question. Here's a kind of question that's posed in the book. You have something like this in one of your homework problems. if the largest of 56 consecutive integers is 279, what is the smallest? So who can answer that?
Please tell me it's 224. I've gotten enough questions wrong.
Well, can you tell us how you arrived at that? Because I'm actually not sure.
So what I did is I basically went 56 back from 279, and I want to say that's 220. I want to say that's 223 if I did my mental math right, and then I added 1 because you have to count like the one you're on too, I guess.
Yeah. Now, did you do all that in your head, or did you write something down?
I did it in my head.
Okay. At some point, maybe it's when you're past 40, you lose your enthusiasm for doing math in your head because it's just too unreliable. Also, it's in the end, you know, even if you can do it in your head, in any situation where you're going to be called upon to do math, it's going to be in a situation where you need to be able to explain to somebody else why what you did works. So let's see if we can figure out a way of so I usually approach math problems with with an eye towards how would I present this solution to somebody else in a way that is clear and convinces somebody, especially even somebody who maybe doesn't understand the problem, it doesn't even understand the question very well. How can you present the solution in a way that will make sense to them? So let's do this. Let's have 279 as our highest integer, and let's have an index that goes along with it. So the index of that is 56. And so 55 would be the number 278, and so on. And so what we want to get to is what's here. So if I do 279 minus 56 would be 223. So so the question is, oops, does 223 go there, or does it go there, or does it go there?
It goes to like a 0.
Exactly. The 223 goes here. So who was that a while ago who said that the answer was 224?
Jana.
Jana, so you're right about that. Now, how do we get that that 223 is supposed to go there? Let's think about it this way. Let me move this down. Six minus 56 would be the number 0. And so that 0 is there. So 279 minus 56 goes there. So there's where that 223 goes. And so that's one way of seeing that that the number that we're interested in is this number 224. Now, this ended up being kind of wordy to explain it this way, but that's okay. I mean, the thing about figuring out how to explain stuff is that you don't always arrive at a really slick presentation or a slick explanation the first time, but it's always helpful. It's a useful skill to try to cultivate, you know, trying to figure out how you present the solution to this to these problems in a way that, again, somebody else can follow. I think if you do this, somebody who doesn't quite understand this, even doesn't quite understand the question, would get it, would get the idea of what are we talking about with consecutive integers. Oh, you can see consecutive integers look like that. And the fact that we're talking about 56 of them means that we're talking about this batch is 56 consecutive integers. Now, you know, when I've graded quizzes and exams before, I'm always, well, it's a very common thing that I'll see students will just simply, you know, they won't try to get their head around some kind of abstract problem like this. I'll actually see students who will write down the entire list of numbers, all 56 of them. So, you know, if you're really a glutton for punishment, you can do that. But the idea is that, you know, what if the idea was to have, you know, 3,056 consecutive integers? Then you couldn't write all those down. So you want to have an approach that works no matter what. Do you have any? Yeah. Now, let's do another example.
Actually, I have a quick question about that.
Yeah.
Does that have anything to do with, and maybe it's like pretty obvious that it does, or what? The theorem 1.1, I think it was, where it was like the n minus m minus 1, because that's kind of how I kind of attached an equation to it, but not really.
Okay, fantastic. It is that. So would you apply that in this case?
Kind of, but then I remember in the video you said not to really trust that. So
Oh,
I didn't want to like have it be that exactly, because that might not work all the time. So I kind of did what Jana did.
Yeah, the thing about that theorem is, you know, for one thing, you've got to remember the theorem, and then you've got to remember what m is, and you've got to remember what n is, and you got to remember if is it +1 or minus. There are all these things to remember. But then, you know, so I find ultimately, you know, if you try to explain this problem to somebody by citing the theorem, they're going to go bleary-eyed as soon as you say theorem, because they're not going to know what theorem you're talking about. They're not going to know where it came from. But then, you know, so you're going to want to be able to explain this way anyway. But then it's fun. It's a good exercise with all of these. Once you've done the problem, to see if can we put it into the context of that theorem. So for this list, this would be our m. It's the index of the smallest number that we want to keep. And this is our index of the largest number that we want to keep. And that theorem would be used to count how many numbers are in this list or how many numbers are in this list. Well, the thing is that theorem is not really necessary in this problem, because we can already see that the number of items in this list is 56, because this is a situation where the list starts with the number 1. So that theorem is not going to be really very helpful. But let's see how that theorem would play out. The number of items in this list is 56, and that would be equal to n minus m minus 1 in the way that I like to think about that. So that would be 56 minus 1 minus 1. So that would be 56 minus 0, so 56. So the theorem is, you know, is true, but it's not really necessary to use the theorem. It would be kind of it's just not productive to try to use the theorem to figure out how many items are in this list, because we already know, because that list starts with the number 1. But that's a great question. And you know, again, about that theorem, there's going to be more instances coming up in this course where theorems are presented, and of course you all are younger than I am. You have a greater capacity for remembering theorems, but even so, remembering a theorem and remembering how it's got to be applied is a lot of work. And I often see students solve problems by pulling some theorem from somewhere and plugging numbers into some theorem, and it's actually the wrong theorem, or they're plugging the numbers in the wrong way or something. So invoking a theorem is sort of a treacherous thing. You got to be careful of. Well, let's do another one where that theorem is useful. So, for instance, before I do another example, does anybody else have any questions or requests?
Oh no, I'm good.
Okay. So question A is, how many two-digit integers are there? Well, you know, this is one that you might be able to pull out of the air just doing your head using that theorem. But again, the idea of wanting to explain it, I think is important. So let me show how I would do this. So the integers that we're interested in are in this green circle. And so I find the easiest way to get that number is this. I look at all the numbers in that blue set, and I subtract the numbers that are in that red set. I don't need to use that 0 because I want to start counting with 1. So I get the total is 90. Now let's think about this in terms of that theorem. Here's our m. Our m is the number 10, and here's our n. Our n is the number 9. And so, oops. So this is our n, and then I've got minus m minus 1. So that really does fit that theorem. Okay, so question B is how many two-digit integers that are multiples of 13? In fact, maybe I'll do this. I'll do, oops, shoot. Maybe I'll do multiples of 8. So let's make our list of integers, but we need to have an index. So there's a bunch of multiples of 8, and the batch of integers that we're interested in is this batch, the two-digit integers that are multiples of 8. So let's think about these in terms of an index. Oops. Notice that each integer is just the index times 8. The batch that we're interested in, I keep choosing the wrong pen. This green batch I can find by I can count this green list by counting this green list. And I can get the number of elements in that green list by counting this blue list and subtracting this red list. So it's going to be, the blue list is going to be 12 items. And I'm going to subtract the number of items in that red list, which is 1 item. And so I just get 11 items. Now we could think of the theorem again. This is our M. Our M is the number 2, and our N is the number 12. So there we have 12. Oops. We have our N, then we have minus M minus 1. Maybe I should color code that. Again, I never trust myself to use that theorem in advance. I only like to use the theorem kind of after the fact to confirm that, yeah, this turns out this does agree with that theorem. There are some theorems that really are kind of without using the theorem, you can't find your way to an answer. But this theorem, I just don't think is that way. I think this theorem is more in the spirit of, solve the problem in a visual way, in some way that is useful for explaining to somebody else, and then check afterwards to see that it does fit the framework of the theorem. I think that's probably a good place to stop. Let me turn my laptop around. Everybody's still there. I think we should probably stop here. I've got a meeting actually starting in a few minutes. Chen Zhao, did you have a question?
No.
Okay. Lainey and Jana, how about you? Do you have any questions or requests?
I think I'm good. This was very helpful. Thank you.
Good. Okay. Well, again, heads up for the video that's coming out today. It's actually it's long because there are a lot of examples, but that's the bad news. The good news is that the math is not terribly hard. It's just that it's I guess it's a sign of how useful the math is that there are so many different kinds of examples that can be where that kind of math is applicable. So it's kind of irresistible. It's hard to stop doing examples because it's kind of cool that they all have the same underlying math. So get started. So that's all to say. Keep an eye out for that video for this afternoon if you like to watch those videos, and get started on tomorrow's homework early, because it's, again, not terribly hard, but just will take a while. So thanks, everybody. I'll stop recording now.
Thank you.
Yeah,
Bye.
have a good day.
You too.
Bye.